The next speaker is Mr. Martin Vandermeer from Fugro. And he's going to talk about the strength of solid data, followed by a number of dots. So I am very anxious about the dots.
Okay, nice to be here. I'm one of those geotechnical engineers, and thinking about cars, there is an engineer that designed the car and exactly knows how the car is. So if we know the dikes as well as the cars, then I think we can do it.
You will not clone the ICT, but you will clone the engineer.
Yeah, probably. I've cloned myself. I have a son. Yeah. Yeah. So, I would like to take you a bit back in time, just looking at data. And not only at real-time data, but stationary data as well. In knowing how high the dike is and what the subsoil is, or what kind of car you got. I'd like to look at some modern ways of collecting data, like aerial data, and trends in that. Problems in just using the data now, in data integration, so not in this future when we have all this artificial intelligence, but problems we are facing now. And something that we are trying to do in another research program, Flood Control 2015. Both Fugro, but also TNO and some other companies are active in that program as well. And I think there is also some cross-contamination possible between these two programs. So looking at water and urban water management is not only about dikes, but also about rainstorms and flushing down big amounts of water down the hills. So you see that you need stationary data sets as well, just to know the terrain. And you can see that there is a tendency to use more and more airborne or satellite data, and it's getting better every time. And just put it into a simple GIS model to have all the data, or to help you to understand land use, or to use near infrared or that kind of thing to get some more detail. It's just physics. And I think that's important to have a base model to add your real-time data to. If the foundation isn't good, I don't think you should build a house. Looking at aerial data, you see that these are getting more common now, so you can get them by plane. Then you can do bigger areas, and you can see that you can use it to find low spots or stuff. This is by plane, so the accuracy is about 10 centimeters. You get 4 dots per square meter. But you can also go to a more high definition LiDAR data set, like what we can do with helicopters. And then you get 3D data models, like this part of the city of Rotterdam. And the city of Rotterdam is measured every year in this kind of parts. And this is not a movie, this is data, so you can do your measurement into this data set. So if the city decides that they want to know something more about the bridge 8 years ago, they go to the data set and do their measurements. So I also like to consider this. Also, this is information, and you could do something with it. And also the modeling is getting more accurate. There is a program, research program, where they try to speed up flood models in 3-dimensional data sets to try to make the SOBAC models 100 times faster. So they get to real time. So also this, I think that's very interesting to consider what this would mean. Another thing that's nice, in the Netherlands, the water boards found out that it could do a lot with LiDAR data, and that all kinds of cities and people can use the data. So in the Netherlands we've decided to fly in the whole of the country with a very accurate data set. So we were used to having, let's say, 1 dot per 16 square meters. And now we have the entire country flown in with 10 dots per square meter. It's not as much as the very accurate data set, but as a base data set, it's very nice. You can do a lot in that. And if you do that every 5 years, the deformation will tell you also something. So I think this is nice. Another thing is that if you want to add data to it with more precision, you can do it by car. So this is an example of the city of Rotterdam. And then you can just get the car and add data to it, because the city will change. Between these 5 years, something will be changing, and that might be important for your modeling of floods or problems with rainstorms, things like that. And I think not only the prediction, it's strange for me to say, of how likely it is that the dike will fail is important, but if you are in some other area where dike is not the main problem, but more you're living on a hill like Manhattan, then you have these kinds of problems. You want to know it also. And looking at some examples of what to do with data, well, we are just, I think, scratching the surface of all kinds of possibilities. But what we try to do is say, well, you always combine data. So you always combine, let's say, satellite data and aerial mapping data. There are more possibilities. So the funny thing on the right is torpedo. It's a geophysical stuff, and that can measure if there's something underneath the surface. So you can find out if you have fresh water or not, or it's getting silty, or you can find minerals. Depending on how you put the instruments in, it will give a fairly good picture of the top layer, but it can go to 800 meters deep. Very modern stuff. And the old-fashioned stuff we have also. So you have to have in-place information like the CPTs or the geobeats or whatever. And you get to some kind of risk assessment, looking at behavior, and you can get to real-time warning. I think it's always the same principle. One trend that we see is one of the problems we are facing still is how to glue all these data sets together. Not only going to real time, but going to area covering, because some of the data is below the water level, some is with helicopter from the top level, and you want to glue these together. This is a picture of data sets glued together for, I think, California dike system. And you want to make continuous subsoil models. Subsoil models are interpreted data, it's not data, so there's geological knowledge in it. You want to cross-check that with other kinds of data, so there I come to the sensor stuff, etc. Because if you predict yes, this should be a weak spot, but the problems occur there, then or your model is wrong or nature is wrong. So you have to check something. These cross-checks are very important. Also, experience is very important. If you just go to a waterboard, let's say this one in Hungary, and you talk to the technical people and you get out their information, their experience, and you combine that, and you glue that knowledge underneath such a digital terrain model, and with their subsoil knowledge already, you're able to get the weak spots out of the system and find out what will happen at certain water levels. So there is already a lot of data and information that you can use. So also these old geotechnical guys, you need them. In looking at how you can combine it, we have put up a system that you can make continuous subsoil models and calculations. And that's one thing that we bring into the program of flood control. So we're testing that out somewhat further. And then you can make safety maps at any water level, given the information that you have on the different mechanisms. And this is a combination of safety checks made directly with very simple algorithms in the GIS, combined with cross-sections calculations, all these dots. Deltares did that one, where you can say, well, what is the slope stability at given conditions? And given conditions is conditions in some extreme event, or conditions now, or a prediction for tomorrow. So this is the kind of models that we are thinking about in getting data that tells us about conditions and transport it to a model and give a safety map. Also, very simple thing, we see that if you go to coastal flooding management, the big thing is to have a city model. Just know where all the buildings are, what buildings are important, what is your critical infrastructure, where is the hospital, what bridge must not fail, which house is on stakes, is high, who is low. The base information is, I think, is vital. This is an example of a city model for Manhattan. So that's flown in. So this is all these skyscrapers, and then they can put over it their idea of critical infrastructure. Buildings they are not sure of their structural integrity in these circumstances, or buildings that are too old, maybe, or a hospital. And that can help the city to find out if they have to check something before the event happens. And that's something that you cannot do by looking at sensors. You're too late. And another thing that you can use is adding it with this INSAR data that you showed also. That you can see, well, I just zoom in and then I find what buildings are stable or not in time. So there is a lot of data that you can use. This is something totally different, but also urban. This is Hong Kong. And then you can see they are not that afraid of dike breaches, but getting the hill on their head. So this is a landslide, and it took down, I think it was 1972. And also these landslides are triggered by extreme rains. So the same events as we fear, but it gets to a landslide. And because it's important, they started to do something about it. So they stabilized parts of the mountains, but also dug in drainage systems, big tunnelings, and we put in a monitoring system on websites with trigger values that tells you what will happen when, and get it on the PDA. But this was 7 years ago. So what are we doing? There's nothing new. It's already possible, I think. And I think the best thing we can do is try to combine all that knowledge also, all these experiences also from landslide risks, and transfer that knowledge to flood risk management, because it's all risk management, and knowing the system. And going to that, I think the program flood control is, I think, is an interesting one as well. You can see there are several parties in it. So like Eikdijk, we have them on board here as well, and ITC, now University of Twente, looking at geophysics, TNO, IBM, Fugro is there, Royal Haskoning, Arcadis, HKV, and we are focusing on three main aspects. That is, what decisions should we make given the circumstances and the information we have, but underneath, what do we know about loads and strengths, and how can we get the way that we have knowledge about hydraulic loads and strengths visualized in such a way that people can decide on it. Because the big problem of these autistic technical people like me is that we know what is happening, but we are hiding the information in reports and all kinds of stuff. So if you want to know it, you cannot find it. So I think there is a big job in visualizing our knowledge in maps and pictures, so people can decide on it. If you want to have something done in time, I think that's important. And the key questions of flood control look very much like the questions that I saw today here. So it's a bit the same program, because one of the questions is, do we know what's happening on location? Let's say the sensors or the satellites. How exciting will it get? The modeling of the strength of the floods that you can have. And what are we going to do? Because not having a monitoring plan is stupid. But having a monitoring plan without an action plan, that's even more stupid. There's no use at all. And underneath, how can Technic help people in visualizing data, etc.? So much of the things that you are doing are alike. I just want to show two interesting cases that we are focusing on to combine our efforts and to make sure that all the parts that we do are coming together. We are focusing on one dike ring in the Netherlands, that's the polder Masterbroek. And we are looking there at real-time hydraulic loads. That's important because it's a funny corner in the Netherlands. We have here this strange thing that should hold back the water, can inflate. And here we have some dike that will be overrun by water, but not everybody agrees if the dike will hold or not, and that will have an influence on the water levels on this one. So there is uncertainty in loads and in models. We will look at dike strength mapping. So can we make a continuous map of dike strength at any condition, with or without traffic loads, or and can we go to real-time strength modules, combining LiDAR data for having this continuous model and numerical models to feed it. That's one. And we want to have an operational system in 2011. So maybe low-tech, but we want to have something running. And the water board itself says, I want to work with it. So I don't want to hear stories about what we can do in the coming 10 years. I want to work with it next year. And that's another thing that we learned. If you make something to be safe in extreme events, we must make something that the responsible authorities will use in their day-to-day business. Because if it is only something that they have to exercise and do when it's really exciting, I think everything is lost, they don't know what to do. So we want to make a system that's also something that will be used in the day-to-day business of the water board, in thinking about management of the dike, their permit policies, etc., etc. If not, I think it's no use. And another interesting thing, so I was glad that I saw your story, is that we are also in touch with the water board, the levee board of New Orleans. We did already a pilot for them in thinking about how the levee boards in the Netherlands use data and do the flood management, and how they work with the information systems, say the state of the art in the Netherlands and something further, and how we can match that with the needs and the different circumstances in New Orleans. So you see here the logo of Delftland is also in there. And we want to look at the typical differences in circumstances, because we are having only storm surge, and our only problem is when and how high it will be. But if you have a hurricane problem, it's different, because it's also where will the hurricane hit the land. And that's uncertainty in place is different. And we want to think about our ideas of levee strength modules and how you can use the same principles for these coastal levee stuff. And what would this typical problem mean for decision support modules as we think of in Holland now. And also in this helps us also to look at our own problem from a different perspective. So I think this is a nice match. And this is really what I wanted to share with you. So I think there is some time.
Thanks, Martin. You gave us a lot of food for thought, but also a lot of food for discussion, I think. So we have still some time left. Robert.
Thank you very much for that. I couldn't sympathize more. A lot of the points that you've addressed, we've also been looking at in urban flood and basically haven't found a solution for yet. So all the points that you've addressed are very topical. So yeah, my main question would be, how can we collaborate on this? How can we solve each other's problems?
Good question.
Well, I think it's interesting to have common cases. Because one of the big decisions that we made this year is say, well, we want to combine all our efforts at one and the same dike ring to prevent that somebody makes a bit of the jigsaw puzzle down there and a bit there, and at the end nothing will fit. So we should try to get some common cases, I think. Everything can be monitored. Yeah.
Practical question. So you mentioned LiDAR technique and the digital terrain models. So are you having all of those for like area around ring dike, digital terrain models? Yeah. Yeah, they are not so easily available. So okay. So can we contact you to?
You look at the AHN, yeah. So that's coming available in parts. So that takes some time. But for instance, for the case that I mentioned, the Polder Mastenbroek, we wanted to have a more detailed model with 40 points per square meter. So for the case, this was flown in. But there is a lot of data everywhere, and my point is, first try to work with what you have, and then think of what you have to add. And in the Netherlands, we know that the AHN is coming available in time.
So
Yeah. Yeah.
I'm missing some 5 parts.
Okay, another question from Robert.
So thank you, Valeria, for raising this issue. So I'll continue a little bit on that, because one of the main issues that we were having is that the AHN data is monitored from the top. So tunnels, bridges, etc., houses are basically all visualized on top. Are you saying that there is data available that has that corrected?
No, I'm saying you have the LiDAR data. You have to fix it because you cannot look beneath the bridge, so that has to be fixed. But if you look at the cities where things are getting more important, you also have the possibility of drive map. So you can add data to that for the difficult spots. You can just glue it. And the big thing is, if you just have to get the car and get a bit of a critical part, that's not such a big job as making a very big project, getting the helicopter on. So I think technology is just progressing, and we have to make models making use of that kind of data. Yeah.
Okay. Other questions? If not, then it's time for tea again. Thank you very much, Martin.